Hello everyone, we are from Massive Data Computing Research Center, Harbin Institute of Technology, and our poster title is Automotive, Utilizing Research Papers and HPO Techniques to Deal with the Cache Problem. Our presentation consists of three parts. The first one is the introduction part. In many fields, a mass of algorithms with completely different hyperparameters have been developed to address the same type of problems. How to help users to correctly and quickly select the most suitable algorithm and hyperparameter setting for the given task instance is a very important research topic nowadays, and this is known as the cache problem. In this paper, we designed the automodel approach, which makes full use of the known information in the related research papers and introduces hyperparameter optimization techniques to solve the cache problem effectively. Our method tremendously reduces the cost of algorithm implementations and hyperparameter configuration space and provides better results. The second part is automodel approach. This is the cache problem definition. As we can see, a set of algorithms should be given before dealing with this problem. In our automodel approach, we try to consider as much algorithms as possible so as to get better results. And our overall idea is to then select the most suitable algorithm A* from them for the given dataset D. Then select the most suitable hyperparameter optimization technique for A* and D. And finally, tune the hyperparameters and get the final result. The major challenge in this pipeline is the first two steps. Since much algorithm should be considered, it will be very time-consuming and expensive. If we examine the algorithms by conducting extensive experiments to avoid the high computational cost, in this paper, we proposed to extract the performance information from the research papers and utilize them to help us to find the A* that we want. This is the overall framework of our automodel approach. It consists of two parts: decision-making model design part, the MD part in short. It extracts the knowledge from the research papers and then builds the decision-making model for better recommendation by using the knowledge that we extracted. And the second part is user demand response part, UDR part in short. In this part, we utilize the decision-making model obtained by DMD part and utilize them to quickly recommend the A*, which is the most suitable algorithm, and then select the most suitable HPO technique to help us find and get the final results. And here is a more detailed introduction of the DMD part. In this part, we aim at getting the decision-making model, which takes the input and output like this. To get this model, firstly, we need the training set, which is the dataset fast algorithm bias. We need it to guide us to make right choices. Besides, we also need select the most suitable features to represent the dataset. To solve the first task, training set. For each dataset, we extract the information, like this, from the related papers, and we use the direct graph to integrate all the informations from different papers. And then we use the reliability scores of each paper to clean the contradictory relations in the graph. Then we finally get the A star that we want using the final graph that we get. After getting the training set, we transform the feature selection problem into an HPO problem and use the classic HPO technique to solve this problem, the task 2. So training set is the most important part in the DMD part. This is an example of the previous steps. In this example, we try to find the most suitable classification algorithm for the one dataset. Firstly, we extract the performance information related to one dataset from the related research papers, and we get this table. Then we set the reliability score for each paper according to these 4 parameters. Then the most suitable algorithm A star for the one dataset should be among the algorithms in this column. And in the second step, we build the graph using this table and use this graph to represent the relationships among these datasets, among these algorithm candidates. For example, paper 1, whose reliability score is 1, thinks that random forest has better performance than J48 on one dataset. Then we get this edge in the graph with weight 1. After getting all potential relations, we can find that there is a contradictory relation among random forest and J48. We reserve one with higher weight and remove the others, and then we get the final graph. Now, the A stars of the one dataset should be among the algorithms in this graph whose internal degree is 0, which means there's no other algorithms performs better than it. Now we get 3 candidates for A star. In the final step, for each candidate, we count the number of algorithms that are proved to have less effective than it, according to the final graph and the table that we get. And finally, we select the algorithm, the candidate algorithm with the most compiled algorithms and consider it as A star. After getting the decision-making model, we can use it to quickly recommend the most suitable algorithm A star, and then we select the most suitable HPO algorithm according to the complexity of the A star, and then we finally train the hyperparameters of A star and get a final result of this cache problem. The third one is the experiments part. We test the automodel approach on cache Weka problem, which aims at finding the most suitable classification algorithm in Weka with the optimal hyperparameter setting for the given classification dataset. We examine the decision-making model that obtained by us And the final experimental results show that the algorithm recommended by our decision-making model exceed over 84% classification algorithms in Weka, which is better than a single classification algorithm in Weka. We also compared our auto model with a classic auto Weka approach on cache Weka problem using these datasets. And the final experimental results show that our method can provide better results in a short time. That's all. Thanks for listening.